Welcome to Module 3 of the Logo PLC training series. In this module, we'll be covering logic gates and their application within PLC programming and a little bit of theory and background on PLCs themselves. Before PLCs, automation was performed using relay logic. By combining relays in different configurations, logic gates could be formed, and these logic gates were used to control machinery in an automated process. The complexity of the wiring and logic made these systems large and difficult to debug, as well as limited in their processing capabilities. The Programmable Logic Controller, or PLC, such as the Siemens Logo, was designed to replace the physical wiring and relays with a method of writing software instructions instead. There are 7 basic logic gates that make up most of the capabilities of a PLC program. These logic gates are the building blocks of how a microcontroller operates. Each microprocessor has millions of logic gates embedded on a silicon die. These logic gates are designed to give the controller the ability to process programs that are input into it. The program consists of user-defined instructions in the form of logic gates. These programs are processed by the logic gates of the microprocessor. To sum up, a PLC is an array of millions of logic gates that are programmable, hence the name Programmable Logic Controller. Logic gates are bitwise operations. A bit is the simplest form of data in the PLC. It is a single value and can either be on or 1 or off, which is represented by 0. A logic gate takes inputs in the form of a bit or bits and applies a logic to it and returns the output in the form of one single bit. It is a simple calculator whereby the inputs are calculated together and an answer is given in the form of an output. There are 7 basic logic gates that are used. These are the AND gate, NAND gate, OR gate, NOR gate, exclusive OR gate or XOR, XNOR gate or exclusive NOR, and the NOT gate. They fall into 3 categories: NOT, AND, OR. The NOT gate is special because it takes only 1 input and the others take 2 or more inputs and calculate them to 1 output each. The AND gate. With the AND gate, 1 and 1 is 1, all the rest are 0. The AND gate needs all inputs to be on before it will turn its output on. This is used, for example, in machine safety, where all the safeties have to be made before the signal for ready is active. Here is a good example. So if my lock on the machine is closed and the door is closed, then you get a ready signal. Otherwise, it will be 0, meaning that the machine is not ready to operate. The NAND gate, or NOT AND gate, is the same as the AND gate, with the exception that all of the outputs are inverted through a NOT function. So if the AND gate would give a 0 as the output, then the NAND gate inverts that to a 1. The OR gate. With the OR gate, 1 or 1 or 1 and 1 will give you 1 at the output. With the OR gate, at least one input must be on for the output to be switched on. This logic could be used where a siren must sound if any errors are active. The NOR gate, or the NOT OR gate. The NOT OR is the inverse of the OR gate, meaning that the outputs from the OR gate are inverted. So if you have a 0 from the OR gate, you will get a 1 from the NOR gate, and if you get a 1 from the OR gate, you get a 0 from the NOR gate. The XOR, or exclusive OR gate. This is similar to the OR gate, however, it will only switch the output on if only one of the inputs are on. So 1 or 1 is 1, but 0, 0 or 1, 1 is 0. This would be used for routing pipes where a swing bend with proximity switches is needed to be either left or right. But if both proximities are on at the same time, then the output would be 0, therefore stopping the process. The XNOR, or exclusive NOT OR, is the same as the exclusive OR with an inverted output. So therefore, if the exclusive OR would put out a 0, that gets inverted to a 1, and if it puts out a 1, that gets inverted to a 0. The NOT gate. The NOT gate takes a single input and inverts it. Therefore, if a 1 is put into a NOT gate, it will put out a 0, and if a 0 is input into the NOT gate, it will output a 1. Now, let's switch to the Logo software to see how these gates work in practice. One of the simplest operations that can be done on a PLC is to connect an input directly to an output. With the Logo interface, you choose the item that you want on the left-hand window and you drag and drop it into the right-hand window. In this case, I'm dragging and dropping an input and an output. It automatically assigns the input to I1 and then works sequentially I2, I3, I4, and likewise for the cues. If something's already being used, then it will just skip that and go to the next available one. So there I'm connecting input 1 to output 1. If I click on the simulation button, there we will see that both are in blue as both of them are off. And if I toggle I1 on at the bottom, they both turn red, indicating that they are both on. Because I1 is on, Q1 is switched on by I1. And there you can see the little light at the bottom indicating that Q1's on. And if I push the switch, I1 is turned off and Q1 turns off too. Let's download this to the PLC in order to see what happens on the physical hardware. I've connected a button up to input 1 of the PLC in order to test what happens when we push the button, and I've connected an LED up to output 1 of the PLC in order to see the output. All 4 of the PLC's outputs have LEDs connected to visualize what is going on. So now that it's downloaded, we go online with the PLC and we put the PLC into run mode. And there you can see the PLC is running. The blocks are blue because input 1 is off, and if I push the button, there input 1 turns on, output 1 turns on, and the LED turns on too. So if I pulse it on and off, every time I push the button, the output comes on. I can also connect many outputs to a single input. So if I put Q2, Q3, and Q4, and I connect them to input number 1, you'll see it forms a link between all 4 of them. And if I download this to the PLC, and then I go online, and I start the PLC, you'll see all 4 lights or LEDs light up when I push the button. Now I will be covering the different kinds of logic gates that you get in the LogoSoft software. I've laid out here an example of a number of different gates, and I will be explaining how they operate. To find the gates, in the left-hand panel of the LogoSoft software under Basic Functions, you'll find the AND gate, the Rising Edge AND gate, the NAND gate, the NAND Rising Edge gate, the OR gate, the NOT OR gate, the Exclusive OR gate, and the NOT gate. If you drag and drop them across, they have different icons, and that helps identify what kind of gate they are. The only gates that I have not covered are the AND Rising Edge and the NAND Rising Edge. To understand these functions, you need to understand how the instructions in a PLC are executed. The PLC starts with the first instruction and runs through all the instructions on the page until it has done each one once. at which point it starts back from the top again. This is called a scan cycle. The rising edge will output a 1 if all the inputs are 1, but only for one scan cycle. On the next scan cycle, it will be 0 again. This is called a rising edge detection. I will now use the LogoSoft software to demonstrate the different logic gates. I'll turn the simulator on. And here we can see the different logic gates. I'll be using input 1 and input 2 to simulate the different logic that you get through the gates. So with both inputs off, 1 and 1 is 1, all the rest is 0. The AND gate comes out as a 0. The inverse of an AND, so 0 inverted, is 1, and the not AND comes out as a 1. 1 or 1 is 1, all the rest is 0 for an OR gate. Therefore, the OR gate comes out as a 0, and the inverse of the 0 is a 1 for a not OR. And with a latching relay, if the set is not turned on, then it will not latch, and therefore it is not switched on. I'll now switch on the first input. And if we follow the logic here, the AND gate, 1 and 1 is 1, all the rest is 0, so the AND gate is still 0. 0 inverted for the not AND is 1. With the OR gate, 1 or 1 is 1, therefore the OR gate is on, and the inverse of 1 is 0, so the not OR is 0. And the set function on the set reset latching relay is set, which means that the output comes on. If I switch this output off, you'll notice that the latching relay stays on. This is because it's latched on until it receives a reset signal on the second line. I'll now turn on input 2. With input 2 on, the AND gate is still a 0 because 1 and 1 is 1, all the rest are 0. The not AND is inverted, so 0 inverted is 1. On the OR gate, 1 or 1 is 1. On the not OR, the 1 coming out of the OR is inverted, therefore it's a 0. And with the latching relay, it's no longer on because we're sending the reset signal to the latching relay. If I turn both signals on simultaneously, you will see that the AND gate becomes a 1 because 1 and 1 is 1. If the output of an AND gate is 1, then the invert of that for the not AND is a 0. On the OR gate, 1 or 1 is 1. Therefore, we have a 1 and a 1. There's a 1 on the OR. And the invert of the 1 is a 0, which is the not OR. And for the latching relay, the set signal is coming through, so it sets, but then the reset signal is also coming through, so it resets it and it comes out as a 0. If I turn off both of these, you will see that's back to the original state. And once again, for the latching relay, if I set it, it turns on. If I turn the output or the input to it off, it stays on until I hit the reset button, and then it will unlatch. Thank you for watching the third module in this Logo PLC series. Please join me for module 4, where we will be covering timers and counters.